fMRI. Activity.
An activity? Yes, please.
Here, see
Never.
me after class.
Okay. I'm sure I'll figure it out.
I'm not loud enough.
Okay, yes.
So, what do you want to talk about?
What's on the
I'm here
test?
to chat with you. What is it you'd like to talk about? Ma'am?
What's on the test?
Okay.
That's always my first question.
All right. Okay. Does someone have a paper copy of the 2012? Yeah?
I think I might.
I could borrow. I don't remember.
I have one. Wait.
One right here. All right.
I'll give it to you if you tell us what's on the test. Wait, this is behavioral.
I can tell you none of these are on the test.
Well,
I can tell you that. All right. So,
as long as it's not what I just have to do with Alex.
number 12 from the 2012 exam. Can I fold this over?
Yeah.
All right, number 12. So we have a first order reaction given a rate constant. Time required for the reaction to be 75% complete. All right. So first off, just a couple things to think about when you're working these. The first thing is to kind of make sure that you're working the right kind of problem. So this is a kinetics problem, and since we're being asked time, right? Since we're being asked for time, we're looking at something involved one of the integrated rate laws, right? We're looking at that. We're not looking at a method of initial rates. We kind of fall into two broad categories. So the first thing we know is that we're the integrated rate law type problem. Now we're told it's first order twice. You're told here, and you're told with the units on K. Both of those tell you first order. It's redundant. Only one of those was needed. All right? And we want to know how long it takes for the reaction to be 75% complete. So there's a couple different ways to approach this problem. All right? So we don't give you a concentration, but realize by giving you this percentage, we've actually effectively given you both concentrations. So first order, one way to do this is you've got your natural log of A times T equals or at time T equals minus KT plus the natural log of A at time 0. Right? Okay, now, to do this, we have a rate constant, so this is minus, we're given 3 times 10 to the minus third inverse seconds. We're asked for time, so there's our time, right? Now, we've got A0 and AT, and we want the reaction to be 75% complete. So when you have this sort of thing, all right, what I do is your initial concentration is A0, and your final concentration, if the reaction is 75% complete, how much A can you assume is going to be there? Right? It's going to be 25% of A is going to be left over. So the assumption is that A is a reactant going to something. All right? We don't know what the reactant is. It doesn't even say. But we have some reactant, and it's going from an initial concentration to some concentration at time t. And if this starts out as A0, 75% complete means 25% of A is left. All right? Which means this right here would be 0.25 times A0. Right? That's 25% of A left over. Everybody okay with that? Is that all right? Okay, so that's what we mean. Sometimes you'll be told some fraction of it is left over, or percentage, right? We've been told 1/4 of A is left, or 3/4 of it is gone. That would be the same information as what we just gave here. So then at this point, now you have the natural log of okay, 0.25 A0 minus the natural log of A0 equals negative 3 times 10 to the minus third inverse seconds t, right? And so this, the natural log of x minus the natural log of y, is the natural log of x divided by y, right? That's just logarithm algebra, if you will. Again, equals your negative 3 times 10 to the minus third inverse seconds times t. You'll notice at this point that that value cancels, right? That's 1. So this simplifies then just to be the natural log of 0.25 equals this value at your time, right? So you go ahead, right? You can take your natural log, okay, 0.25, all right, which is minus 1.3862, etc., right? You're going to divide by a negative number, so we're going to get rid of the negative sign on that, because the negative is coming over from here. We're going to divide this by 3 times 10 to the negative third, and get a t of, all right, and we have, so your 3 sig figs is what's going to come out of here. And then you're going to end up with 462. You divide it, so that's going to be seconds. All right? 462 seconds. Is that okay? Is that how that works? So that's one way to work this problem. Okay? With these kinetics problems, there's often 2 ways. So the other way to think about this, all right, is come back to this. This is one of those special numbers. If you're thinking about your reaction, now let's think about half-lives. If the reaction undergoes 1 half-life, how much of A would be left? 50%, or 0.5 A. If it then undergoes 1 more half-life, how much is left? 0.25A. So we are actually looking for the time after we've done 2 exact half-lives. And do we have an easy way to figure out what the half-life of a first order reaction is?
6.693.
That's right.
Over.
Remember the half-life, T1 half, for a first order reaction is 0.693 divided by K. So 0.693 divided by, we have 3 times 10 to the minus third inverse seconds, right? And then you're going to take this times 2 half-lives. So 2 half-lives times 2, and you're going to get that answer. Right? So that's one of those special values, 75% complete, all right, is 2 exact half-lives. So either way, this will always work. Always make sure you can go back to the integrated rate law and use that full method. All right? But sometimes you'll have a shortcut you can take like this. Okay. Good? Yes. All right. Yes. Same one. Number 15. Okay. At a given temperature, you have a mixture of benzene. All right. We're given a vapor pressure for benzene. That means benzene's volatile. The fact that we gave you a pressure means it's volatile. Okay. And toluene, vapor pressure. We've got 2 volatile species. All right. We have a mixture of those, a solution. The mole fraction of benzene in the solution is 0.59. Assuming ideal behavior, calculate the mole fraction of toluene in the vapor. Okay? So we're being given information, okay, about the solution. And we're being asked to calculate a mole fraction in the vapor phase. Okay? So the first thing to realize, if you have two species, A and B, benzene, toluene, and you mix them together, all right? Which of those is more volatile, by the way, based on these two numbers? Benzene or toluene? Which is more volatile? Benzene, because it has the higher vapor pressure. So at a given temperature, you'll have more benzene being generated, escaping to the vapor phase, than you will toluene. All right, so that's the first thing to realize. So if you make a mixture of benzene and toluene, okay, it turns out that the benzene, the more volatile species, is going to have an easier time escaping the liquid and getting to the vapor phase. It's more volatile. Okay? So ultimately, when you look at the vapor phase will be enriched in the more volatile species. Said a different way, the more volatile species will have a larger mole fraction in the vapor phase than it does in the liquid phase. Okay? This is what we use. We use this property in petroleum refining plants to separate different petroleum products. These giant columns is called a fractional distillation, where you count on the fact that things have different vapor pressures, and the more volatile one you'll be able to extract first. So you can pull them apart by different vapor pressures. Okay? So people make tons of money using this property. All right? So, having said that, how in the world do we go about getting this? All right. Now, if we look at what we have, we're given a mole fraction, so we're told, so let's just walk through here. So we have the vapor pressure, the P0 of benzene, which I'm just going to call B, all right, because toluene then will be T. So this is 7.54. The pure pressure of toluene, we're told, is 294. Okay? And we're told the mole fraction of benzene in solution. Okay? So I'm going to say this is in the liquid phase. All right? The mole fraction of benzene is 0.590. Right? If that's the case, what's the mole fraction of toluene in the liquid phase? Can you do that? What is it? 0.41. Everybody okay with that? 1 minus this number will be the mole fraction, because you add the two mole fractions together, they should equal 1. Right? So we know this. All right? Now, how do we go about getting the mole fraction in the vapor phase? We go back to a trick we learned in the ideal gas chapter. And we learned this. We defined mole fraction of something. Okay? So we want to know the mole fraction of times. The mole fraction of toluene. Okay? We just think about mole fraction. It's going to be moles, or N, the moles of toluene, divided by total moles. Everybody okay with that? That's just the definition of what mole fraction means. Moles of T divided by total moles. All right? Turns out that we can relate this to pressure, because we have PV equals nRT. I'm going to bring this over here. So I have P equals nRT divided by V. So I just rearrange the ideal gas law. So pressure is proportional to moles. So what I'm going to do, and since I've got N here, what I'm going to do is bring this over here. So then that would be V divided by RT. Okay? So I'm just going to move it over, so bring the V up and the RT down. So N equals P times V over RT. And what you can do is plug that in here. So what that means is that the moles of toluene, okay, is going to be the pressure of toluene times V divided by RT. And the total pressure, well, is going to be, the total pressure down here is the moles of toluene plus the moles of benzene. So the moles of toluene is the same thing, PT V over RT, plus right? Moles of benzene will be the pressure of the benzene, V over RT. With me so far, right? Now, remember that these are in one container, it's a solution, so the volume's the same here, R's the same, they're at the same temperature. So you can factor your V over RT out. So this is pressure of toluene, V over RT, divided by, down here, PT plus PV, and I'm going to pull a V over RT out of there. Those cancel. They're the same value, right? And what I have is PT, and the addition of the two partial pressures is the total pressure. That statement right there, that this equals those two, that's just Dalton's law. So we end up with this statement that the mole fraction of a gas is going to be its partial pressure divided by the total pressure. Okay? That's how you can calculate the mole fraction in a gas mixture. We talked about that last semester in the gas law chapter. So I just need to get PT and P total. So to get those, I need the pressures of these two individual things. So the pressure of the toluene is going to be the mole fraction of toluene times its pure pressure, right? And the pressure of benzene is going to be its mole fraction times the P0 of benzene. Okay? So this is going to be, so the mole fraction of toluene, we were told, or we calculated, that's 0.410 times P0, which is 290. Okay? And that's in torr. Okay? This one here is 0.59 times its pure pressure, which is 745 torr. Okay? Right? So then we just calculate those two values, 0.41 times 290. So this is 118.9, 3/6 alkaria extra, torr. Okay? And this one is 0.59 times 745. And that one is 439.55, again, 3/6, 4. Okay? So your P total equals plus 118.9. Okay? And that's going to be equal to 558.45. All right? So your mole fraction right here is just going to be the total, the pressure of toluene, which is 558.45. Sorry, it's going to be 118.9 divided by the total, okay, which is 558.45. Okay, times 118.9, and I end up with 0.213, which is, sorry, A. Okay? Everybody clear on that? You don't have to do all of this. I just wanted to show you where this equation comes from. This is something you should remember from your Gen Chem 1. So think about this, right? What we have is that the mole fraction in the liquid phase of toluene. So this is the mole fraction, and I'm sorry, just being clear, this is the mole fraction of toluene in the gas phase. So we had the mole fraction in the liquid phase. So in the liquid phase, toluene was 0.41. In the gas phase, it's 0.213. Toluene is the less volatile species, so its mole fraction goes down. Benzene's mole fraction would be larger. Benzene's mole fraction is 0.787. It's higher than it was. Okay? Yes? DFW. Black t-shirt, DFW. Are you okay? Is that good?
Yes, thank
All right.
you.
DFW.
Thank you.
All right, thank you. I'll make sure I answered her question. Everybody clear on this? So be comfortable with how to calculate mole fractions, pressures, and everything in the liquid phase, but how to relate it to the pressure in the, or the mole fraction in the vapor phase. Okay? Yes, ma'am. 17 on the same test. We're going to work our way through. All right. Did anybody do any homework, by the way? How many people did homework? Be honest. A few?
I'm getting that.
All right. Just checking. Look at that one. Another Raoult's Law problem. So the following diagram, okay, shows the relationship between vapor pressure and solution composition, i.e. mole fraction. All right? So, mixture of A and B. So based on this diagram, which of these is not true? So we haven't put everything into the diagram, but realize that by labeling, putting one label here, I know everything else in here. I could have put a piece of information there or a piece of information there. And then you know everything in this diagram. All right? So this is a two-component Raoult's Law diagram. So let's just look at this line right here now. So this is the Raoult's Law. All right? This right here is the pressure of A, which is its mole fraction times P0A. That's what this line right here is. Okay? So the mole fraction, when the mole fraction of A is 0, the pressure of A is 0 down here. There's no A when there's no pressure from A when A has no mole fraction. When it's pure A, then the value up here, you plug a 1 in for mole fraction, and then the pressure that comes from A is A's pure pressure. So this value right up here, now I can draw on it, mole fraction of A, 0, 1. This is P0A. So this is the pressure of A at each point. Okay? Now, what's this other line here? This other line here, remember that the mole fraction of B goes the opposite direction. When the mole fraction of A is 1 over here, that means there's no B. When there's no A, it's all B. So this right here is P0B, and this line is the pressure that comes from B at each mole fraction. Everybody okay with that? Yes? So just by knowing that, now, I could have given you just this value, or just that value, or either one of these. And with just one of those, you can fill all the rest of this in. You should be able to. Okay, we expected you to do it on this question here. All right? So some questions before we get to the question that's asked in the problem. Which species is more volatile, A or B? A, because it has a higher pure pressure. Which one has stronger intermolecular interactions, A or B? B, because it has a lower overall vapor pressure. Okay? Now, the line across the top is your Dalton's law. This is the total pressure, which is PA plus PB. So at any point, we pick this mole fraction, that value there came from, so kind of drawing a dotted line here, it comes from this value right here for PA, this number, and then this number is PB, and when you add this plus this, you get that value there. So that's just Dalton's law across the top. Okay? All right. So that's what the diagram has, what it tells us. So now let's look at the questions. We leave this diagram all labeled, and we'll do this. Okay. So we're looking for which one is false. Which statement is, which of the statements below is not true? All right. So we're looking for the false one. The process of forming the solution is favored by entropy. What do you think? We're looking for false. Is that true or false?
True.
That's true, right? Entropy is the drive to disorder or randomness. Every solution process is favored by entropy. every solution process is favored by B. Okay? That's not an answer. The substance with the higher normal boiling point is A. Is that true or false? See, that's false, right? The higher normal boiling point will be the one that's less volatile, which we said was B. So, statement B is false. Statement B is false. C, the substance with the higher pure vapor pressure is A. Yes, we said that. This number is bigger than that number. At any mole fraction that we pick, the substance that will be enriched in the vapor phase versus the liquid phase is A. We just did a whole problem on that. A is more volatile, so at any point we pick in the vapor phase, the mole fraction of A will be bigger than the mole fraction of A was in the liquid phase. So that statement is true. We just did that problem and proved that. And then the substance with the stronger intermolecular forces is B. Yes, because it has a lower vapor pressure. So B is the one that's not correct. Okay? Is that clear for everybody how those work? You can get a lot of information with just that one diagram. Yes?
What does enriched mean again?
Enriched means that it has a, when you enrich something, you increase how much of it you have in there. So there's more A in the vapor phase than you have A in the liquid phase. It's enriched, means its mole fraction is bigger in the vapor phase than it is in the liquid.
So there's actually more content of A.
It's a higher concentration of A in the vapor.
Oh, more concentration. Okay. Thank you.
Higher concentration in terms of mole fraction. That's right. Okay. Yes.
Can you go over how to find the rate law from like the table? So like I guess number 6 would be an example like
On this one? I will. Let me put that. Are there any other questions on this problem? On this problem? Let me ask you this. One other question. So the solution between A and B, is it an ideal solution or not? Is the solution between A and B that's described by this diagram, is it an ideal solution or not an ideal solution?
It's ideal.
Ideal?
Yeah.
Why? He's correct. He said it's an ideal solution. Absolutely. Why?
Because it behaves along the lines of the normal changes in solution, the boiling point, the freezing point decreases, and there's more technical terms I could use, but
So,
I don't know them all.
so that's not the definition of an ideal solution. So it does all those things, but any solution that we make is going to, at some level, follow those things. But there's a very specific statement for what it means to be an ideal
it
solution.
obeys the law.
I'm sorry?
Like it obeys the law, like Reynolds law.
It'll do what?
It
Say it again.
obeys Reynolds law. Like,
Obeys, not, yes, and actually it obeys Raoult's law, exactly. Ideal solutions obey Raoult's law. Raoult's law is a straight line. So what you have here, this is a straight line described by this. This is a straight line described by put a B, a B, a B, and that line is there. The fact that those are straight lines, straight as I could draw quickly, all right, means that this is an ideal solution. Thermodynamically, what does it mean for a solution to be ideal? Do you remember? It would have been the first thing we talked about in the solutions chapter. My section. You guys should know this. Yes?
is it like on the diagram when like 2 lines going up, like a little 1 line?
That's exactly what it is. Remember when you looked at thermodynamics and we wanted to talk about the delta H solution, taking a solute and a solvent, putting them together, making a solution, and we said there's a different path we can take. Delta H is a state function. So we can go straight from mixing them to make a solution, or we can break solute interactions. Remember that was endothermic, so that was a pharo. Then we broke solvent interactions. That wasn't a pharo. And then we put the expanded solvent together, and that was exothermic, came down. And an ideal solution is one where this arrow plus this arrow going up are exactly equal to the one arrow coming down. Meaning that the strength of the intermolecular interactions in the solute and solvent are comparable in strength to the strength of the interactions between the solute and the solvent. The solute and the solvent have very similar interactions. So delta H of solution equals 0. That's an even more technical definition of an ideal solution. Okay? Now what happens, we're not going to test you on this. We used to cover this in our textbook. We don't anymore. This diagram changes if you have an exothermic or an endothermic solution process. So if delta H of solution is positive or negative, you don't get straight lines anymore. They become curves. Don't worry about it. We're not going to go into that. But this diagram changes if it's not ideal. So the straight lines only come when it's an ideal solution. Okay? Yes?
How did you identify that the upward sloping line was substance A and downward?
How did I figure this out?
No, the line under it, the
This
upward.
one?
Yeah. How did you figure out that that was substance A but not B?
Question is, how do I know that this was for substance A? Look at the mole fraction. Mole fraction of A goes from 0 to 1. So if the mole fraction of A is 0, there's no A there, so it's pure B, right? And you'll notice that this line is down here. It should be at 0. It should be all the way down and touching here. So if there's no A, there's no pressure coming from A. When the mole fraction is 1 for A, the pressure is all the way up here, and it's the total pressure in the system, so that would be the P0A. Okay? So the mole fraction tells you which is which. Which is which. The other way to do this would be not to label anything and to give you like information E. Tell you that substance B has stronger intermolecular forces. Here's a diagram, label everything. Right? Nasty, but you should be able to do that. It's not that bad. You should be able to do that. Okay, other questions about Raoult's law right now? This is kind of conceptual. Problem 6?
Yes.
Problem 6. All right. Can I get an ask? Can I hang on to your exam for a while and use this?
Yeah, go for it.
Appreciate it. I didn't ask. You should have asked. All right. So we have a reaction, some random reaction up here. The following data collected at constant temperature. Okay, remember that's important because temperature affects rate. How does temperature affect the rate of a
It
reaction?
increases.
What does it do? Where does it impact it in a rate law? K. K is temperature dependent. Remember that's the Arrhenius equation. K equals A times E to the negative EA over RT. That's where the temperature effect comes in. It changes K. All right? So we're doing this at constant temperature. We want the rate law for this reaction using this data. So this is again called the method of initial rates. What we have are experiments or trials, right? Where experiment 1, we take a container, we put this amount of A, this amount of B in it, and let the reaction run, and we measure the initial rate. And there it is. Then we take it, empty the container, we put this amount of A and B in, and then run a new reaction, measure a new rate. We change concentrations, the rate changes, right? And based on how those change, we can then figure out what the rate law is going to be, right? So first off, let's cover everything else up. Bless you. Let's write the generic rate law. So what's the rate law going to be? Just kind of a generic one. What do we know right away?
K
It's going to be K,
A B
bracket A, bracket B, bracket A, yeah, plus or times?
times.
Times. People, there's a small percentage of people that will put pluses in here. This is all product. Everything's multiplied. So if the concentration of A, what's our exponent?
X.
Yes, we don't know, so we'll put an X. And then the concentration of B to
Y.
Y. Now technically we could go ahead and put the concentration of C and the concentration of D, but typically C and D products don't impact the rate. They can. In biochemistry you'll learn this, that products often act as inhibitors. Something will be made in the body and you don't want too much of it, so the stuff that gets made starts feeding back and shutting the reaction down. And so in that case, then the product would be affecting the rate. But usually it doesn't, so we usually only put the reactants in. All right? That's typically what we're going to do unless you have reason to believe otherwise. So now we want to get these exponents. So what we want to do is go in and look at the data. And so let's look at the data, see if we can just do it by inspection. Not have to do any fancy math. All right, so what we're going to do is we're going to look at 2 experiments here. The first 2 experiments, I'm keeping B constant, and I'm changing A. So what we can do is look at the impact that A has on rate. So we are going after X, right? So I double, going from 2 to 1. So if I go from here to here, I doubled A. And what happened to the rate? It increased by a factor of what?
4.
4. Just take this number divided by that number, okay? And you get 4. So when A doubles, the rate increases by 4. So what's the exponent X?
2.
2. Is everybody okay with that? You double the concentration times an exponent of 2. 2 squared would be a rate change of 4. Okay? So we know that X is 2. We'll just put that right over this. All right? And now we want to find 2 experiments that keep A constant. So let's compare 1 and 3. And so when we double B, A is constant. Double B, what happens to the rate law? It doubles. And so they're proportional. The rate is proportional to B. So Y is 1. So that means the rate law is K times A squared times B. Everybody okay with that? Double. Everybody understand how we did that? Pretty straightforward?
I have a question.
Yes.
So we don't have to divide the concentration?
The math method of doing this?
Yeah.
You don't have to. So like that long equation where we put the rate law and the rate law and divide the
Right.
one by the other. So what's being asked here is you can do this. So the idea would be, let's take these first 2. Remember the mathematical way, if the numbers aren't real clean, the way you can figure this out is we're going to look at these 2. So what you do is I'm going to write the rate. So rate for trial 1, okay, equals K times the concentration of A. Again, let's say I don't know the exponents. B to the Y, right? So, and then I'm going to divide that by this one here. So the rate statement, rate law, written out, again, here, X and B, Y. So if I substitute everything in, what I'm going to have is, I'm going to have 6 times 10 to the minus second equals, I don't know K. A is 0.2 to the X, and B is 0.1 to the Y, right? And then I'm dividing that by this experiment here. So I've got 1.5 times 10 to the minus second equals K times, this is 0.1 to the X times 0.1 to the Y. Everybody okay with that? So I just set that equation up. Well, this works out really easy. This divided by this is 4. K divided by K is 1. 0.1 to the Y divided by 0.1 to the Y is 1. So now I'm left with 0.2 to the X divided by 0.1 to the Y, to the X, which is equal to 0.2 divided by 0.1 to the X, which is equal to 2 to the X. So what value of X makes this true? 2, which is what we got there. So that's the technical, that's the mathematical way that you can get to any exponent. Is you set up, you put these 2, I always set it up so the bigger rate's on top. That's the way. It'll work if you put the bigger rate on the bottom, you'll just be dealing with decimals or fractions. I'd rather work with bigger numbers bigger than 1. All right? But we didn't have to do that. You can, but that's a lot of work, and by eye we could figure out. You should be comfortable with seeing those directly proportional, increased by a factor of 4. You should be able to see those. All right? If you do that, you save a lot of time with the math. Okay? So, you good with that so far? So, I think that's all they wanted you to do. So here's the rate law. So, K, 2, and 1, so it looks like it's B, right? And then if we wanted to, we could then go ahead, and just while we're doing it, let's go ahead and calculate the value of K, just to do it. So I've got a rate equals K times A squared times B. How do I go ahead and get the rate constant K? Anybody? Blah, blah, blah. What?
Plug in values for the rate, the chemical concentrations, and then divide the rate by the...
That's right. I take any one of your experiments and plug them in. We didn't use 4 yet. Let's use experiment 4 up here. So what you would have, the rate is 2.7 times 10 to the minus 1 equals, I don't know K. A is 0.3 quantity squared times 0.2. Okay? So working that out, your K is going to be equal to, all right, so I have 3 squared times 2.
Yeah, I know, but they're
Times
clean.
2.7.
And I lost her.
And I end up with 15. All right, 3 sig figs everywhere, so 15.0. And our units. So what you have here is you have molar squared, right? The unit here is molar, and the units over here are always molar per second. All right? So the way to get just molar here is I've got molar cubed, is that I need to have molar squared in the denominator, right? So if I have molar squared here, molar cubed divided by molar squared will give me molar on the left side. And then you'll always need to put seconds in the denominator because these don't have time, and the units on your rate is always molar per second. So that unit there, it's the same as saying molar negative 2 seconds minus 1. All right? Okay? So that's how we would get the value of K. Just plug one of them in, bless you, and then calculate it. And you should get the same value of K approximately. Might be a little bit of experimental error, but you should get the same approximate value for K. It doesn't matter which of your experiments you pick. Okay? All right. So follow-up questions about rate, method of initial rate. Okay. Number 14.
Number 14, yes.
Okay. We'll take a look at it here in a second. Other real quick questions about, we're going to go look at another one similar to this first. But questions about this? Yes?
Can you use the phase of the order of reaction only if we know this one reactant? Like 1 over x of this order,
Yep.
but only if you know one reactant? Or
No. This right here, these units here tell me that the overall order is third order. 2 plus 1 is third order. So the units will tell you what the overall order of a reaction is, even if there's multiple reactants.
So the 2, so in the M and the S, the 2 plus 1 is 3, and the overall order is 3?
Yes.
Oh, okay.
So the order of this reaction with a light just went up, right? So the order of the reaction with respect to A is 2. The order of the reaction with respect to B is 1. And the overall order is 2 plus 1 or 3. It's third order overall. Yes. And the units on K will reflect that. These are the units for a third order reaction. You don't know on the units. If you know the units on K, what you don't know is if this right here with A and B, what you don't know is, does that mean that this is a 3 and a 0, or a 2 and a 1, or a 1 and a 2, or a 0 and a 3? You don't know that from the units, but you know the overall order is third order. So you'd know it'd be one of those scenarios.
that's what I think.
Okay, good. All right, which problem are we going to look at now? 14. All right, one other on this?
Yeah, one thing. Why are things first order, second order, or zero order? Or do we have to know that?
So why are some reactions
Yeah,
zero?
I get how to work with them, just why are they that way?
Well, it depends on, it ultimately depends on what the chemistry is, what the reaction is. A first order reaction, okay? For example, so I can give you, best way to do it is to give you examples. So an example of a first order reaction is radioactive decay. You have an isotope, and we'll talk about nuclear chemistry right at the end of this semester. But radioactive decay happens because you have an atom whose nucleus is unstable. Turns out the number of protons and neutrons, it's a bad ratio. You don't have enough neutrons probably. All right? So anyway, it's unstable, and so that one isotope will sit there, and at some point, which we can't predict when, it will break down, kick out some energy, maybe a particle, and go to a lower energy state. But it doesn't require colliding with anything else. All it depends on is that species sitting there and being unstable. So it's first order. It doesn't require a collision. That's a first order. A second order reaction, the easiest type of second order reaction to think of is just having like two A's or an A and a B collide. A simple collision is second order. If it's two A's, you need two of them to collide. If it's an A and a B, you need two things. So that's a second order. Zero order is the one that's a little more difficult to understand. But a good example of a zero order is, let's say you have, and I'm not going to dig it out of here, but let's say you have a reaction, a gas reaction, and it's two A's go to B, all right? And they're gases. But the idea is that if you just take your two A's and mix them, it takes forever for the reaction to occur. It doesn't occur, or it occurs very slowly for some reason. So what you do is you add a catalyst, something like platinum. So platinum, solid surface chemistry. So what has to happen is the A's have to come down, and once they end up on the surface, then they can interact and the reaction go. So a platinum surface can be a catalyst. It makes the reaction go faster. Now, how's this zero order? Well, the two A's have to end up on the surface. So you start putting more A in. A's start landing on the surface and reacting. As you increase the concentration of A, you're going to saturate the surface of the platinum. You're going to fill it with A molecules. Once you've filled the surface, there's no more places for an A to land. The reaction now becomes independent of how much A gas you put in. So at that point, when the surface is saturated, the reaction is now zero order. It doesn't matter if you double the amount of gas out there or triple it or whatever. The reaction is only happening on the surface. That's a zero order. Okay? So those are examples of those three types of reactions. Okay? Yes?
So go back to the thing we just did with finding K.
Yes?
I might have been looking too much into this. It looked like the table said that that rate was per minute.
Did it say per minute? You are right. So this would be per minute, thank you. Okay, per minute. Whew. Yep, just, usually it's seconds. This one was per minute. Thanks for correcting that. Okay? All right, problem 14. Oh, another table. All right. Decomposition reaction. So I've got this reaction here. Here's initial rate data. So initial concentrations, initial rates. All right. Different experiments. What is the rate constant for the reaction? So this, to get K, well, first thing, well, what we have to do is you need to know what the rate law is and be able to plug values in, right? So this is like both steps, like we just did. You first get a rate law, and then once you know the rate law, plug things in. So first off, we look at this. So I know that the rate law for this is K times RS squared to some power x, right? Now I look at this. So if I go through and you can look at these experiments, right? Everything is changing. right? But let's see, do we have a nice one? 2 and 4. So if you look at experiment 2 and 4, when I double this concentration, what happens there, right? What is that? So that's, you take 0.438 divided by 0.109, and you end up with this divided by this is 4.0183, which is 4, right? So when you double the concentration, the rate increases by a factor of 4, so X is 2, right? So that's our rate law. So now we just take any one of these experiments. Let's take this one. So 0.0394 molar, this one seconds, equals K times 0.150 squared. Solve for K, right? Just rearrange this and solve for K. I can go through and do that, but you see how to do it, right? You just crank through. What are the units on K going to be? This is a second order reaction. So what are the units on K going to be? It's going to be inverse. It's going to be molar minus 1, seconds minus 1. So I bet we can rule out some answers, right? So we can rule, this is liter, so this is inverse moles, molar, inverse seconds, inverse molar. No, we can't. They're all right units. All right. Sometimes we'll do that, but some of the units will be wrong, and that'd be an initial cut you could do to make it easier, but you just have to plug the numbers. Okay? Now, say that again. The 2014, so spring 14. I don't have it on. Do you have it on? Does anybody have the spring 14 exam? Thank you. Which problem? 15? Okay. All right. I'm hanging on to your exam still. So
Okay.
There's going to be more questions. All right. 15? 15? All right, 15. What mass of sodium chloride is needed to lower the freezing point of 500 mils of water by 10 degrees? And you're given the density of water. Okay? So, reading what this is, we're lowering the freezing point. The change in the freezing point is 10 degrees, which means the freezing point of that solution is minus 10 degrees, right? Yes? So we're lowering the freezing point by that amount. So this is going to be the molality, right, times Kf, which is molality. The number, you're given this number, 1.86 degrees Celsius per mole out. That's in your useful information. You'll get that useful information. Everybody okay with that? So the first thing you can calculate, given this real change, right? So we can do our 10 divided by 1.86. And what you end up with is that to get this change, you need the molality of your solution to be 5. I'm just going to write some extra sig figs here. Right? You need it to be 5.38 molal. Is everybody clear on that? That's the actual concentration of particles necessary to get a 10-degree change in your freezing point. Yes? Well, we might end up using it. You've got an equation like an I times M, right? This is the actual molality. This is the real molality of particles, right? I haven't taken dissociation into account yet. I don't use that. In my class, I actually told people, don't memorize that equation. A real delta T gives you a real molality. This is the better way to think about it. I know what the actual molality of particles are.
When would you use
We're going to get there. Let me keep working. I like excitement. Yes. No, we'll give you a table that has boiling point, freezing point, Kf and Kb for different solvents, including water. Okay? Most people know 0 and 100, but in case you forget it on the exam, we've got it on there. All right, so we want to know what mass of sodium chloride is needed to lower this. All right? Now, thing is, so this is the concentration. Now, we are not being given, this is the actual concentration. We weren't given what concentration, like we weren't told that we made up like a 4 molal solution and this is the actual molality calculated, right? So what are we going to assume the Van Hoff factor is then? What do we assume? The only thing we can do here is make an assumption. So what are we going to assume the Van Hoff factor is for sodium chloride?
2.
We're going to assume it's 2. We know it's probably less than that, but this problem is assuming 2. All right, we're assuming it's completely, that's the best we can do. All right? Because we're not given any information anywhere that tells us exactly how much sodium chloride we actually put in. That's what we're trying to solve. Yes?
So how do you know when to use the Van Hoff factor? Like,
So when do you
Or how do you
use the Van Hoff factor? If you're given information, so we're given a delta T, which gives us an actual molality. And then, so what if I was told that, if this problem had been reworded, and you were told that you made up a 4 molal solution of sodium chloride, a 4 molal solution, and you measured a delta T of 10 degrees. What's I, right? So in that case, this is the actual molality of particles, including whatever dissociation occurred. The solution that you made was 4 molal, assuming no dissociation. That's what that number was. So then you take this number divided by 4, and that would be I. Right? This is the concentration of particles due to dissociation. That's that delta T gives us the actual molality. We're not given any information about what we really made up, what we thought the concentration was. So we have to assume that I is 2. All right? So this concentration here, right, is assuming that you had 2 particles there for every sodium chloride. So this divided by 2 would be the concentration of sodium chloride, right? Because if we made a 1 molal solution of sodium chloride, we would expect a 2 molal solution of particles. So this actual concentration is twice as big as the sodium chloride solution we're making up. Okay? So this then is going to be the moles of sodium chloride divided by the kilograms of water. All right? So the moles of sodium chloride I don't know. We're trying to figure this out. We're trying to figure out grams. But the kilograms of water, right? I've got water is 1 gram per mil. So if I have 500 mils, this number is kilograms. So it's going to be 5.5 kilograms in the denominator there, right? 500 grams, 1 gram per mil. So 500 mils is 500 grams, which is 0.5 kilograms. Everybody with me? So now I can calculate moles. So the moles of sodium chloride I need are going to be 5.3763 divided by 2, right?
2.6.
Times 0.5. And I end up with 1.344 moles of sodium chloride, right? And then I take that number, and I know that 1 mole of sodium chloride is, you look up the molar mass, can we just leave it at that, right? And then the molar mass times that will give you, and this is in grams, so this number times this, the moles cancel, this times whatever the molar mass is will give you the grams of sodium chloride you need. Okay? Got wrinkly noses over here. Is it okay? Clear? Yeah? Where did I get the 2? Again,
Van Hoff factor.
the fact of the matter is sodium chloride has a theoretical Van Hoff factor 2. Every 1 sodium chloride I put in, I get 2 ions. Right? So the actual concentration theoretically would be 2 molal if I made a 1 molal solution. Right? So this is the actual concentration. So the concentration of sodium chloride units would be half this number, theoretically. And that's the best we can do. That's why you divide that by 2, and then you just get moles, and then convert moles to grams by using the molar mass. Formula mass. Yes? Yes?
What's a situation where we wouldn't have to use that?
Say that again?
What,
When would you not need to like divide by 2 or something? If this had been a sucrose solution. If it's a non-electrolyte, then there's this concentration, the actual molality would be the molality you made up if there's no ionization or dissociation going on. Yes?
So if we're ever getting something that's not as simple as salt, they're going to give us the Van R factor, or just say that it doesn't?
Or it'll be, or you would be expected to know what it is,
Okay.
right? Like I could give you, if we were trying to calculate exactly what I is, I could give you a weak acid HA, right? Weak acid, if you make up a 1 mol solution of HA and it's a weak acid, what you know is that the actual concentration of particles is bigger than 1 mol and less than 2 mol. And you don't know what that value is. But if you were given the information about what the actual change in your colligative property is, that would allow you to calculate the actual concentration, and then that number is your actual concentration. That 1 mol is what you made up of that acid. This number divided by that 1 mol would give you then the op, how much it actually dissociated. Okay? Yes? Dial it. Because this is the, work it the opposite way. Think about it the opposite way. I give you a certain amount of sodium chloride. You're going to put it into 0.5, so you take the mass of sodium chloride, you're going to convert it to moles, right? Then you're going to take the moles of sodium chloride divided by 0.5 kilograms, and that's going to give you a molality. But that's the molality of sodium chloride with it not dissociated, right? To get it, the concentration dissociated, you then have to multiply. So this number here, the moles of sodium chloride that you calculated, divided by the kilograms, would give you a number which is half of this. And then you would have to multiply that by 2 in order to get what the actual molality is of particles. So we're working the other way, so we have to divide by 2 to take that into account. Okay? This is good stuff. This is important stuff. Other questions on this specific question? I forget who asked it. Good? Yes? Next question. Yeah. Yes. 25. All right, so we want the osmotic pressure of a solution that contains 0.049 grams of a hydrocarbon solute dissolved in benzene, there, to make 350 mils of solution. Okay. All right, so we're calculating osmotic pressure. Remember, osmotic pressure is pi equals molarity times R times T. That shouldn't be a real hard equation. This is just P equals nRT divided by V. This is the ideal gas law rearranged. Moles divided by volume is molarity. And then we rename P pi, which is a pressure. That's all the osmotic pressure equation is. It's the ideal gas law. That's all it is. All right? So nothing new there. All right? But we want pi. All right? So we have 0.49 grams of your hydrocarbon. Okay? So this is going to be, well, the molarity is going to be 0.049 grams. All right? And we know that 1 mole of this is 340 grams. So there's the moles. All right? Moles of solute divided by liters of solution. Okay? We're making 350 mils of solution. So So this is 0.3500 liters. That's molarity, because that's the molarity of this solution. R is 0.08206 liter atmospheres per mole Kelvin. Okay? Your liters cancel there. Here's your moles, they cancel. And then we need a temperature, 20 degrees, so that's 293.15 Kelvin, right? 273.15 plus 1. You have to convert that to Kelvin so that your Kelvins cancel, and what we're going to come out with is something that's in atmospheres. We'll convert the torr later, okay? Your answer's in torr here. We'll worry about that later. Is everybody okay with that setup? Let's just plug and chug. So let's do that. So I've got 0.049 divided by 340, okay? Divided by 0.35, just so that you know this is a 0.0004118 molar solution. 368, sorry. So anyway, I've got that number times 0.08206, all right? Times 293.15. So I have a pressure of 0.009905. Got 2 sig figs actually, so we're going to have 2 sig figs there. Atmospheres. Right? That's the units that come out of this. All right? And then I need to convert it to torr, so I know each atmosphere has how many torr in it? 760, that's exact. So I take that number times 760, and you end up with 7.5 torr. Answer D. Okay? Yes? 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 Good?
Instead of comparing to ATM or like equal ATM, I was trying to see the R that goes with 4
314? Okay.
and I messed
So, yep, it's because that's the wrong R. So she said what she used here was a different R. She used 8.314 joules per mole Kelvin. That's the other R. There's problems here, right? The problem is that you've got joules, which is an energy unit. There's no energy here. So your joules don't cancel, right? Things don't cancel. Again, come back to this. Look at this equation here. It's the ideal gas law, so you're going to use the R that you used for the gas law, so that your units all cancel. This R is the R that you use in the Arrhenius equation. If you have to do an Arrhenius calculation, right, Arrhenius equation calculation, this is the R that you use. You'll get both R's on the equation. You've been getting both values of R since we introduced the ideal gas law. Or, yes, since we introduced it. Okay? Sir? I'm sorry? Yeah, new question. Let's do it. 33 on chapter which one? 33, so 1333.
No, you're talking
Awesome.
to yourself.
All right. Put this up here for now. I don't know what to do. We've got a homework question. 1333. All right. You guys didn't see that Dr. McAfee just poked his head in the back. I think he was taking attendance for his class. No, I'm just kidding. Did he leave? Did he not? Okay. All right. He won his class. Okay. Talking about how excellent an instructor you are. Yeah. All right. So 1333. So we have solubility of potassium nitrate is 155 grams per 100 grams of water. That's kind of a normal concentration unit for solubility, is grams of solute that will go into 100 grams of solvent. All right? And this is the temperature, and this is how much goes in at 25 degrees. So we want to know what mass in grams of KNO3 will crystallize out of solution if exactly 100 grams of its saturated solution is cooled to 25 degrees. Okay? Of its saturated solution. All right, so you pick a tricky one, wouldn't you? All right, good. This one we got to do a little bit of thinking about. All right, so the idea is that the tricky part, if you will, is that we have 100 grams of solution, right? And so if we have 100 grams of solution, right, this is going to equal X grams of potassium nitrate and 100 minus X grams of water. Everybody okay with that? Is that okay? That's what we know, is that we have this. All right? And so this is what we start out with. X grams of potassium nitrate and 100 minus X grams of water. All right? And what we do then, all right, so thinking this through, we have 100 grams of the solution, so we start out with this, and that's at the 75 degrees, and it's cooled down to the lower temperature of 25. All right? So the max, so once we take it down to 25, right, then what we know is that, let me think. So if we take it down to 25 degrees, where it's 25 degrees here, then we know at 25 degrees that only 38, that's interesting, 75. So this is 155 grams go in at 75, 38. So this one becomes less soluble as you increase the temperature. So that's one interesting thing about this. Anyway, so once we take it down to the lower temperature, we can have a maximum of 38 grams. Yeah. Let me think about this.
Professor?
Yeah.
Did you say it becomes more or less salt?
It goes from 155 into 100 grams at 75 degrees. It drops to 38 grams at 25. So it's interesting. It actually becomes, oh wait a minute. It becomes, at 25. So that's right. It's less soluble at a lower temperature. So this is the, okay, right. Okay, so what mass in grams will crystallize out to exactly 100 grams of the saturated solution is cooled 25 degrees. So we start out with 100 grams, and then when we cool it, we're going to have some amount drop out. 100 grams. So that's 100 minus X. I'd have to think a bit on this one, figure out how to do this one. This is one we assigned? Awesome. No, it's doable. I'm just trying to think about the way to set it up. The concept of solubility is on the test. That specific problem is not on the test. Okay. So, good job. I don't see too many of these anymore where I have to stop and I'm not quite sure what to do on the spot. I'm not sure. I'll have an answer for you. Come see me tomorrow. So, I'm not sure. I'll work it out and I'll post it for you. I'll post it on my website. Okay? Yeah, that's good. That's a good problem. Awesome. No, I kind of like it when because I don't find these too often anymore. I've done so many of these. I pretty much know how to solve all the problems. So every once in a while, yeah, I'm not quite sure how to set up the ratio right Here, if we had started out with, yeah, I've got to think about this one. I've got to think about this one. Yeah. Pardon?
Dr. Dieckmann, can I have my test back?
You want your test back?
Yeah. Thank you.
Which one did you have?
2012.
There you go. Thanks for letting us use this.
No problem.
There you go. We're going to move on, and I will post the solution to this. If you ask a question, email me, and I'll let you know. All right? So I'm going to work it out kind of offline, and I'll come back and give you the answer. All right? So, yes?
Can we work out number 5 on this, please?
5 on this page. Where did this come from?
SI.
SI. These are SI problems. Awesome. All right? Okay. So at 298, the osmotic pressure of glucose, piece of paper here. All right. So at 298, the osmotic pressure, so pi, equals 10.5 atmospheres. Okay? And we want the freezing point of that solution. Okay? And we've got the density of the solution is that value there. So here we have the value of pi, so the osmotic pressure. This is molarity times R times T, okay? And we're given at 298, so we can calculate, so this is molarity times 0.08206 liter atmospheres per mole Kelvin, right? And the temperature we're given is, even nice, it's in Kelvin. So with this, what we can calculate is what the molarity is. And then we want a freezing point. So once we have the molarity, then we can go fold that in as a concentration unit and calculate a delta T. So this gives us a freezing, molarity. So if we go through, and glucose is a non-electrolyte, so it doesn't dissociate or ionize, right? So the concentration that comes out is the real concentration. So 10.5 divided by 0.08206, all right, divided by 298, and we end up with a molarity of 0.4294, let's do 938, do an extra 6 big there, all right? So this is the molarity, right? And this is the moles of glucose divided by liters of solution. All right? Just to let you know. All right, so that's what that stands for, molarity. Now, if we want the freezing point, right? We want the freezing point. We're looking for the delta TF, and we're putting this into, you're not told, so you're putting it into water, right? So to calculate that, I need a molality times the KF. So what I have to do is, this is now a unit conversion problem, where I have to convert from molarity to molality, which is moles of glucose divided by kilograms of water. Okay? So this is now a unit conversion problem to get the molality, and And then once I have molality, then I can plug it in here and get a delta T. All right? So if this is my concentration, okay, so writing it down here, so I have 0.42938, okay, molar, okay, that's going to be 0.42938 moles of glucose, okay, per 1 liter of solution. Okay? Now, so I need to get from here, that's my unit expanded, right, to this. So I need to get, here I have moles of glucose. Okay? So I have the units I need there. Okay? But what I need is to get a kilogram, how many kilograms of water I have in this. So the other piece of information, anytime you are going from molarity to something else, or from something else to molarity, if molarity is involved, then you have to have a density of your solution. So I have a liter of solution, and you're told that the density, so the density is 1.16 grams per mil, all right? I don't have a mil, I have 1,000 mils, okay? So if I have 1,000 milliliters, the question is how many grams is that, right? And then that will give me grams of solution, right? So I have 1.16, right, times 1,000. Okay? And so what you end up with then is 1160, right? I'm going to put the sig figs are right there. This is how many grams of solution I have in order to have this many moles of glucose, right? Now, I need kilograms of water, so this is the grams of solution, okay? And if I subtract from that now how many grams of glucose I have, I'll know how many grams of water. This is glucose plus water. So they give you, so we have to calculate the molar mass of glucose, so it's 6 times 12.01 plus 12 times 1.008 plus 6 times 16, okay? So what you end up with is, I screwed it up, so 6 times 12.01 equals plus 12 times 1.008 equals, all right, then plus 6 times 16 equals, so this is,
180.
glucose is 180.156 grams per mole, right? So I take this number here, okay, 0.42938 moles, right? And I have 180.156 grams per mole. That's going to tell me how many, so times 0.42938, right? So I end up with 77.355. Again, got like 4 sig figs, 1, 2, 3, 4. This is how many grams of glucose. So I'm going to subtract that from this to figure out grams of water. This is how many grams of, right here. This is how many grams of glucose. That many moles is that many grams. This is the grams of solution. This minus this will give me grams of water. Okay. Plus 60. And so I end up with 1082.645, right? And last sig fig was 12 was there. So there's actually my last sig fig, because that was a subtraction. This is how many grams of water I have. So this calculation for then molality, right? Molality of this solution is going to be moles of glucose, so 0.42938 moles, divided by kilograms of water, 1, 2, 3, so 1.0826, right? There's my last sig fig. This is how many kilograms of water I have, all right? That's the molality. So if I take that as my molality, remembering up here I wanted a delta T. So the molality times Kf, Kf for water is 1.86 degrees Celsius per molal. That's going to be the delta T for this solution, right? So I'm going to take 0.42938 divided by 1.0826, right? And then times 1.86, right? And I end up with a delta T of 0.7377, okay, degrees Celsius. So your freezing point of this solution is going to be what?
0. Wait,
For the
freezing?
solution. The freezing
Oh.
point for your solution will be 0, water 0, 0 minus this number. So your freezing point, your TF,
The same.
will be minus 0.738 degrees Celsius. Okay? So this problem involved first using your osmotic pressure to get a molarity, a unit conversion to get molarity to molality, and then the molality to calculate a delta T and then a T. A lot of steps, but each step you should be comfortable doing. Okay? And when you're in doubt about what to do, right? If you're in doubt what to do, go ahead and just start doing whatever calculations you can do. Right? We know, since I know pressure and I know temperature, I can get a molarity. And then you can start thinking your way through most problems, kind of figuring out, you know, then we wanted this, then I saw that this was a unit conversion, etc. Okay? So your SI gave you that. That's good. SI's doing their job. That's an awesome problem. Next question. It's not even 10 o'clock. We've got another whole half an hour scheduled. Here you go. Thank you. Yes, ma'am. So 1368. Have vapor pressure, right? We have the vapor pressure of pure water. So we have T0 of water, right, is 23.76 torr. Right, the millimeters of mercury are torr, so I like writing it that way, it's easier. Okay? And the pressure for seawater, which is a solution, is 22.98 torr. Okay? So we want to know the molality of the seawater, assuming that all of it is just sodium chloride. So first off, does this make sense? So we've got pure water, we dissolve salt in it, and the pressure's lower. It should be. There's a vapor pressure lowering when you dissolve stuff. That's one of your colligative properties, right? So that's Raoult's law. So this goes in the right direction, all right? So what we can do is, given these two values, right, Raoult's law says, is that the pressure of the solution, we're assuming here, you have to make an assumption that, well, yeah, this is my only solute. So water is the only thing that's creating the pressure, right? So the pressure of the solution, okay, which is going to be the pressure that comes from water in the solution, is going to be the mole fraction of water times the P0 of water. Everybody okay with that? All the pressure above the solution is coming from just the water. All right? So we know this number here, this is the solution is the seawater. So this number is 22.98 torr equals the mole fraction of water times, and this value is 23.76 torr. Okay? So if we do that, and we just take 22.98 and divide it by 23.76, we end up with a mole fraction, right, of water of 0.9672. Right? 4 sig figs there. So, oh, you can't see that, sorry. Got the water out. So there's your mole fraction of water. Just Raoult's law. Pressure is equal to the mole fraction of it. And you'll notice in Raoult's law, again, the thing to be careful of is when you're calculating using Raoult's law, we're used to concentrations like mole fractions being associated with how much solute is in the solution. But the mole fraction here is the mole fraction of the thing that's creating the pressure, which is the solvent in this case. So you'll notice that in Raoult's law, and that's why I always write it out. Everything in the Raoult's law equation is pertaining to the same thing, the volatile species. Okay? The pressure, we can already tell you that the pressure associated with sodium chloride is going to be 0. It's non-volatile. Okay? How do you know in a problem if a species is volatile? What do we have to give you? Yeah, we have to give you a P0 for it, right? To know that it's volatile. We know sodium chloride is not volatile. All right, so now we have a mole fraction, but we wanted a molality, so now this is a unit conversion problem. All right? So mole fraction, what this tells you, and let me take this down just a little bit here so I've got some more space to work here. So mole fraction of water, which is 0.9671717, okay? This is equal to, okay, this is the moles in. This is the N of water divided by N of water plus N of NaCl. All right? Everybody okay with that? That's what the mole fraction is that number. Okay? So if we assume, all right, so we have that. So we have to make some assumption here because we weren't given an exact amount of anything. What we know from these two pressures is this mole fraction. So what I can do is I can assume that if this total value is 1, then this number is this. So this mole fraction is the same 0.9671717 moles of water divided by 1 mole total. This plus this equals 1. Everybody okay with that? That divided by that is that number. So this number, so this is 0.9671717, right? Moles of water divided by, well, then it's going to be 0.9671717, okay? Moles of water plus, right? Well, 1 minus this number, right? So plus 0.032828 moles of sodium chloride, right? And that is, again, sig figs are there. 1, 2, 3 is up there. All right? So I'm sorry. So 1 mole total, you take this moles from 1, and that's how much is left. So this is how many moles of sodium chloride we have in that solution. This is how many moles of water. Everybody okay with that? That's what that mole fraction means. And now we want to convert that to molality. Well, the molality will be the moles of sodium chloride divided by kilograms of water. Okay? So we know now the moles of sodium chloride at 0.032828 moles of sodium chloride divided by kilograms of water. Okay? Well, I have this many moles of water, right? So if I have this many moles of water, I'm going to write it up here. So 0.9671717 moles of water, right? And 1 mole of water is 18.016 grams, right? So the moles cancel, so I can convert this and figure out how many grams that is. So 0.9671717 times 18.016. And so what I have is this is 17.4 0.025 grams of water. So that many moles of water is that many grams, and I need it in terms of kilograms. So then this is going to be 0.017425 kilograms of water. Right? And so then I just have to take this divided by this, and that's my molality. So 0.0328828 divided by 0.017425, and I end up with a molality of 1.88. It's 1.88 molality. Okay? So again, this looks ugly, but again, think your way through it. Given, it's always good once you work a problem, is don't just ignore it. Go back and what did you figure out from it, right? Given a P0 and a pressure, you had to interpret that this is a solution. The difference here, right? This plugs into Raoult's law to give you a mole fraction, and then basically you wanted a molality, so it's a mole fraction to molality conversion. Okay, we just put a little bit of a front story on it, talked about it being a seawater solution. But we could have given that problem to you just saying, here's a mole fraction, convert it to a molality. And then just go from there. So these are good problems to be able to do. What you should be able to do is go through. Now, we can't go to molarity because we weren't given a density of the solution, I don't think. But if you were given a density of the solution, then you could go to molarity. You've got mole fraction. You should be able to go to mass fraction. You should be able to go to parts per million, parts per billion, right? All of those units are available to you. Molarity, we don't have a density, so you can't get to it. But once you've got one of these, if you're not comfortable with unit conversions, go ahead and go to the other conversions. You can just do it. Create a problem, extra practice to make sure you're good at those. All right? Yes?
Just remind me another temperature, like depression, freezing point problem.
Not at all.
Associates the underlying formula solution.
So this is solution. So is this problem? Yeah. Okay. Yep, thank you. Okay, what is the molal concentration? Get this out of the way here. So we want to know what is the molal concentration of the solute in solution. Okay. So you just want to know the delta T for solution one? Is that right? Is that what you wanted to do here?
I kind of guess I was confused when you were talking earlier about when you were talking about dissociation. You said don't memorize Van 't Hoff equation. Basically,
Okay.
are you dividing the molarity and
Right. So basically, what you'd like me to do is calculate what the freezing point would be for this solution.
Yeah.
Okay. So we're not doing this exact problem. We're taking solution one and calculating a freezing point for it. Good enough. We can do that. All right. So we don't need all that stuff above it. All right. So we have a 0.05 molal solution of calcium chloride, CaCl2, and I want to know the freezing point. All right? So we need to know the so if we're going to do this, right? Blow this up a little bit here. Right? We know that the change in the freezing point is going to be the molality times the Kf, right? Which is molality times 1.86 degrees Celsius per molal. You're given this for water, right? So I need to know what the molality of that solution would be. So this is the molality, right? But what we assume, right, for this is that calcium chloride will break down into how many, or dissociate into how many ions? 3. So your concentration here won't be 0.05 molal, it'll be 0.15 molal. So this would be So this is going to be 0.15 molal times 1.86 degrees Celsius per molal. Okay? So again, you're not given any other information. To know what the actual, how far this actually dissociates, you would have to know delta T. This information tells you how far this actually dissociates. We're calculating this, so then you have to use the theoretical I. The theoretical I for potassium chloride is 3. It dissociates in. So yeah, so this concentration times 3 is the concentration of particles.
Will we have to deal with partiality, like, once that's partiality, or will we gonna see that?
But yes, you will, but to do that, what I'd have to give you is different information. I would have had to tell you, for example, does everybody see this? Given this now, we can calculate the delta T, subtract that from 0, that's the freezing point, right? So that would be the theoretical freezing point. Now, let's say, let me just do that calculation real quick so I can tie this in. So let's say, so I have 0.15 times 1.86, all right? So the freezing point of this delta T is 0.279. So the TF for this solution is going to be minus 0.279 degrees Celsius. All right? So that is the actual freezing point. Let's say, well, this is the theoretical freezing point. Let's say that the actual freezing point that you measure is minus 0.21 degrees Celsius. Right? So that's what you actually measure. All right? So given that, my delta T freezing, the actual value for this, not the theoretical one that we would predict if it's completely dissociated, but the actual value for this is going to be 0.210, right? And that value is going to be equal to the actual molality in solution times 1.86 degrees Celsius per molal, right? So the actual molality, okay, is going to be your 0.21 divided by 1.86. So the actual molality of particles in solution is 0.1129 molal. Are you okay with that? Everybody okay with this so far? The actual freezing point tells you the actual molality in solution. So you made up a 0.05 molal solution, but what you got out of it was a 0.113 molal solution. So based on this compared to that, you can calculate what the actual Van Hoff factor is. So the I, the actual Van Hoff factor, is going to be your actual molality, which is 0.1129, and divide that by what you made up. This is assuming no dissociation, 0.05. So you divide this by 0.05. And you get an I of 2.26. So it didn't dissociate completely. If it had dissociated completely, your I would be 3, and your delta T would have been 0.279. But it wasn't. So an actual temperature, or an actual delta T that you measure, gives you an actual M, an actual molality, which you can then relate to what you made up to get the I. Now, realize that there's an equation that you may have memorized in the book, which was the delta T is molality times I times your T times your KF here, right? Well, the molality that's in there is this number right here, what you made up. And the I would be this. So this number times that number is that number. Okay? But I break it apart. I like thinking that an actual delta T gives you an actual molality. And now I can go back off and use that and figure out what I want to do with it. If I want an I, then I just divide that actual molality divided by an undissociated molality, and I get it. Okay? Good? Yes?
So like here we, like you multiply the I times the 0.05, and like the other problem when we did, like that was similar to this, you divided it by the I. Like how would you know?
We were going opposite. We were doing something kind of different in that other problem. I don't remember which problem, what we were doing in the other problem, but we were going a different direction, I think. Well, actually, so the idea here is, let me think. So we had calculated here what I did was if you do cross multiplication, right? I could take this number and bring it down here. These you can swap them through cross multiplication. So you could bring this number up here. So the actual concentration would be this divided by the Van Hoff factor, which was what we did. We wanted to know what was the concentration, that was it. We wanted to know what's the concentration of sodium chloride that we made. So we were solving for this number right here. So just rearrange this. You cross multiply, right? So think of this being over 1. This times this equals this times this. So I can switch these positions, and I can say 0.1129 divided by the Van Hoff factor equals 0.05. Okay? So what we were trying to calculate was what's the undissociated concentration. We had measured an actual delta T, or an actual molality, and so we divided it by the theoretical I to get what that concentration would have been. So we're just solving a different thing there. So they look similar, but we're just solving for something different. Same direction, actually. Yeah. Okay? Is that good? Yep. Okay. Yes, sir. On 1986? Okay. All right, the decomposition of N2O into an O2 is a first order reaction. So N2O into an O2. So I need 2 of those and 2 of those. All right, so that's balanced now. All right. The decomposition of this is first order. And at temperature, the half-life of the reaction, so I have a T1 half equals 3.58 times 10 to the third minutes. Remember that it's a first order reaction, so this is equal to 0.693 divided by K. So anytime you're given a half-life of a first order reaction, we basically gave you K. Right? All right. So if the initial pressure, so N2O0 is 2.10 atmospheres at this temperature. Calculate what we want is the total gas pressure after 1 half-life, assuming a constant volume. All right? So this is going to be kind of a 2-step process, okay? At least 2 steps. So the first thing we can do is after 1 half-life, all right, what we'd like to know is how much of this is left. That's what we usually calculate, right? We'll start out, we were given information, we're told how much of this we start with, and then after a certain amount of time, we'll know how much of this is left, right? So if you know that, we can use stoichiometry to figure out how much of this and this we produced, right? Because let's say that we lose, well, we start out with a certain amount of this after 1 half-life, right? Let's think about it. If we're doing, well, it says after, calculate, all right, so the initial pressure is this. Calculate the total gas pressure after 1 half-life. So after 1 half-life, right, let's just do this, write this down. 2 N2 plus O2. So after 1 half-life, we started with 2.10 atmospheres of this. Okay? And remember now that PD equals nRT, so pressure and moles are proportional. So we can do the stoichiometry with pressure. We're keeping temperature and volume constant. So I could, if I wanted to, right? I could go through and ultimately convert these pressures to moles. and then do stoichiometry. But you can actually relate it through the pressures as well, okay, because they're directly proportional to each other. Okay? This is constant, this is constant, and this is constant. Volume, R, and T are being kept constant, so pressure and moles are directly proportional. So I'm not going to convert to moles. All right? So I'm starting out with this. I'm assuming I don't have any of these. After one half-life, if this is where I start, at the end of the reaction, how much of this is left after one half-life? How much? 1.05 atmospheres. Everybody okay with that? That's one half-life. I go to half the initial. This was my initial. I go to half the initial. All right? So that means that the amount of this, the change, I lost 1.05 atmospheres of this. Right? If I lost 1.05 of this, how much N2 did I create? For every 2 of these, I get 2 of those. So if I lost 1.05 here, I produced 1.05 atmospheres here, and this would be 1.05 divided by 2. Right? Does everybody see that? This is just stoichiometry. For every 2 of these I lose, I make 2 of these and make 1 of those. So I lost in this time period, right? I went from here, I ended here, so this is how much I lost. So this is how much I lost. Same amount of N2, same coefficient, and then this would be half that, all right? So the final amount of this that I have would be 0 plus this, or 1.05, and then the amount of this I would have would be 1.05 divided by 2. And those added together is your total pressure. Is everybody okay with that? So it turns out we didn't even need the half-life time and everything. We didn't need K. This one was totally stoichiometry. Good. Got a bunch of people here sitting with their arms crossed. They're not looking really happy. Oh, now they're uncrossing their arms. They're looking really stern. You okay with that? Yeah, now they're smiling. Okay. All right. I'm just teasing you. I like teasing. Good. All right. Yes. 13 on 2012. That she walked out. Yes. 13.
It's right here. If you want the paper.
I'll use the paper version. That way I can- Although, yeah, you can hang on. Which number, 12? Did you say 12? 13. Okay. As I get older, my attention span decreases. There must be some kinetics equation that relates that age to attention span. All right. 13.
Ignore my writing.
Okay, so 23 degrees, right, at 23 degrees, the vapor pressure of acetonitrile is 81.4, while the pressure of acetone is this. So I'm given 2 vapor pressures, okay? Those are both volatile. What's the vapor pressure of a solution where I mix those together? And I'm assuming it behaves as an ideal solution. All that says is assume I can use Raoult's law. I get straight lines. All right? So let's just cover this up. Always cover up your answers. Get your answer and then find it. Don't look at answers on your calculator and go do this. All right, so I've got acetonitrile. Oh, they're both ACs. Oh, okay, fine. All right, I can't use my abbreviation. So the pressure of acetonitrile, I'm going to use an N for. All right, so this is going to be the mole fraction of the acetonitrile times the pure pressure of acetonitrile. The pressure of the acetone is going to be the mole fraction of acetone times the P0 of the acetone, right? So this is going to be, contains 0.55 moles of acetonitrile, so acetonitrile, so it's going to be 0.550 moles of acetonitrile divided by 0.55 plus 0.35. That's the mole fraction, and the P0 for acetonitrile is 81.4. All right? And so let's just get that number, and then we'll know what the mole fraction is for the other one. So we have 0.55 plus 0.35, right? That's 0.9 times 0.55. So this number here is 0.6111, right? So this is going to be, it's going to be what, 0.3999? Yes. Right. So this mole fraction times 184.54. Okay. All right, so this one pressure is going to be, so we have 0.6111 times 81. So we have 49.5, right, torr. That's the partial pressure of the acetonitrile. Partial pressure of the acetone is 0.3889 times 184.5. This is going to be 71.75 plus 0.495. So, can't do that. 49.5 plus 71.75, right? And that's 121.34. So we rounded it 3 sig figs, so it's 121. So the pressure of one, the pressure of the other, there's the total pressure.
Can I take a picture of your 2012 exam?
Is that okay? Yes?
Fine.
Now, if I wanted to know the mole fraction, if I cared about the mole fraction of acetonitrile in the vapor phase, the mole fraction of acetonitrile in the gas phase, it would be the partial pressure of the acetonitrile, 49.5, divided by the total pressure, okay? 49.5 divided by 121.3. And the mole fraction up there is going to be 0.408. So in solution, sorry, this is the less volatile species, right? And so in solution it's 0.6, and in the vapor phase it's only 0.4. So the less volatile thing is decreased in concentration in the vapor phase. So that's just reminding you. You don't have to do that for this problem. Just reminding you how to calculate here. This is partial pressure divided by total pressure gives you mole fraction in the vapor. Okay. Yes.
Can we do a problem where it talks about the intermediates in rate law? I think it's on
So
the
a mechanism?
Yes, please. Thank you.
Do you think there's one in here that does that?
I believe it's on the last page.
This one?
A little higher.
Intermediate?
The other one above it.
Above?
Yes. That one.
Oh, at the top here?
28.
Okay. All right, so we have this mechanism, all right? And we want to know what the rate law is for the overall reaction. So what's our strategy? This is our mechanism. How do we figure out what the overall rate law is going to be?
By the units?
Sorry?
Units?
Nope, not by
No?
units. We look at slow step. Remember, in a mechanism, the slow step is the rate determining step. So if you're told this is the mechanism, you're not asked to validate it. If this is the mechanism, then you go to the slow step, so the rate is equal to NO quantity squared. We can do that, right, for elementary steps, because elementary steps describe individual collisions. So we know exactly the molecularity, if you will, how many things are reacting, so we can predict the exponents in that rate law for an elementary step. If I add these all together, right, your overall reaction is going to be what? Let's do that. So I've got 2 NOs. All right, so I have 2 NOs. I've got N2 and N2 cancel. I've got hydrogen and hydrogen, so I've got 2 H2s. N2O and N2O, those cancel. I have water, water, so I have 2 waters on this side, and I have an N2 on this side. Does that balance? 2 N's, 2 N's, 4, 2 oxygens, 2 oxygens, 4 hydrogens, 4 hydrogens. So there's the overall reaction. I just added these 3 together, right? So what's the rate law for the overall reaction? Well, if you don't know this information, right? If I don't know fast and slow and I just added these, or if you were just given this as the overall balanced reaction, you would say that the rate law is K times NO to the X power times H2 to the Y power. That's what you know if it's just an overall reaction, right? But given that this is the mechanism, I can say that the slow step, the rate law for this is going to be, so it's K times NO quantity squared. So what that tells me is that the exponent on X is 2 and Y is 0. The reaction doesn't depend on H2. Why? Why doesn't it depend on H2? Because there's no H2 in the rate determining step. Without the mechanism, you don't know that. See, that's the problem. If you're just given the overall reaction, we don't know that hydrogen, H2, isn't part of the rate determining step. Once you see the details of the mechanism, we know that H2 doesn't have to do with the slow step. It's one of the fast steps. In this reaction mechanism, now that we have the overall one, what's the role of NO? Reactant, product, intermediate, or catalyst? NO. It's a reactant because it's a reactant in the overall reaction. How about H2? It's a reactant. Water's a product, N2's a product. You look at the overall reaction to determine reactants and products. How about N2O2? What is it? It's an intermediate. It's not there at the beginning. It's created and then goes away before the end. So it's not there, shows up, and then goes away. How about N2O? How about N2O? It's another intermediate. It's not there at the beginning. It shows up, and then it goes away. So we have 2 intermediates in this. Do we have a catalyst? No. No catalyst in this. Okay? The catalyst would be there at the beginning, go away, and then at the very end it would show up again. Catalyst intermediates do not show up in the overall balanced reaction because they're in 2 places. They cancel. A catalyst, though, has to be in the rate determining step because catalysts affect the rate. So whatever the slow step is will have the catalyst in it. Has to. Okay? Is that good?
Yes, thank
A
you.
lot more. Gave me a chance to go through some stuff that some people, I know my group only saw today. Dr. McAfee's class probably looked at that, what, 2 weeks ago? He's not here to appreciate it. Other questions? Yes, ma'am.
Could they be listed in any order?
Could they be listed in any order? Well, now, when you add them together, they add up. They'll add up to the same thing. But the order kind of implies what's the order of things happening. You would still, if you put them in a different order, you would still get this as the overall reaction, but you would be implying something else happened first. Because see, if you did that, if you put this one first, you would be starting out with N2O2, but you don't have any N2O2 first. You have to create it in that step. So there is an order that you need to have. Yes? Yes, for each one of these, we're not given it, but each of these reactions is endo or exo, and the overall reaction is endo or exo. If you're given a potential energy diagram, you could say which is which. Or if I told you endo, exo, whatever, you could draw a potential energy diagram for it. The diagram would have 3 bumps in it. No, it turns out that we didn't go over this in class, but there's a case where the second step is slow, the first step is fast, and that you have to use a different procedure to figure out the rate law. It's called the method of initial rates, where you have to, because what happens is your second step's a slow step, so the second step usually has an intermediate in it, and your rate law can't have an intermediate in it. So then you have to take the first step, it's usually an equilibrium, so the forward reaction and the reverse reactions have the same rate, so you write the rate law for the first forward reaction, a rate law for the reverse reaction, you set those two rates equal. And then you solve that equation for the intermediate, and then plug that into that equation for the second one. And then you combine constants, and you'll usually get the overall rate law. Yeah. No, the book doesn't have that detail. It has a problem that it asks you to work. You had both of these, right? Thank you so much. So the book doesn't have it, but are you in my section? So the packet that I gave you, the last.
The 2014. Oh.
Just to show up. Thanks. If you look at the last page, not the last page. Oh, this is a different one. So this you're in sideways. Oh yeah, thanks. No, do you have? Look at the last page right here. The method of initial rates is called the steady state approximation. So fast, slow. So what happens is when you write this is a slow step, so here's the rate law for the slow step. This is an intermediate. You can't have an intermediate in the rate law. So when you look at this, this is the experimental rate law. This is what you have for the slow step. They don't look equal. But this has an intermediate in it. So what you have to do is first take the first reaction. It's an equilibrium. So you can write the forward rate. The forward rate is k times this to the first power. The reverse of the first reaction is k times n over R2. And then these two rates are equal. So you set this equal to this. You're doing this to get rid of that. So solve for this, bring k reverse over. Now you have this is equal to this thing. Take that and plug it in here, which is what we did here. The k, that's just a constant. Then you have NO times NO, that's NO squared, there's your BR, and now those two are equal. The experimentally determined one and your rate law, now they're equal, as they have to be. It's just that when you look at for this step, when the slow step is a second step, the slow step has an intermediate in it, so you have to do some substitutions to get the intermediate out of it. So that's there. We're not testing you guys on that. But the book actually has a problem working, the homework may even have a problem like that, but we're not testing you on the steady state approximation. But that's what happens like in biology, this happens quite a bit. In enzyme kinetics and all, you'll see this quite a bit in biochemistry.
Specifically, like for the rate step, is it the first one?
Yeah. You'll see what's called the steady state approximation. It's called Michaelis-Menten kinetics. It's enzyme kinetics. When you get into that, this is the hallmark of it, is the steady state approximation. If you go on and take biochemistry, you'll see lots of that. Yeah.
Should we know the factors that affect the reaction rate? Like enthalpy?
Well, like, what do you mean, like, so it's temperature and concentration?
Yeah.
Like
those
things that affect
affected,
the collision?
But enthalpy doesn't.
Enthalpy doesn't. Enthalpy doesn't. What happens is,
That's like the curve.
right, but if you think about the curve, you've got this diagram, like, so let's say we're here, right? The beginning, the reactants, potential energy, products, that's thermodynamics. It's in between, it's the size of the hump, the activation energy. That is the kinetics part. That's the thing that determines rate. And then temperature, and then concentration. Yes, correct. Say that again. Say that again.
Okay. The mechanics of, or like the process of the activation energy density.
If you change the activation energy, how can we change the activation energy? What do we have to add? Talked about it today, last day in class. We would have talked about it. What do you add to change activation energy? Starts with a C and ends with catalyst. All right?
Yeah, that's what I'm confused
Yeah,
about.
you add a catalyst, it makes the bump smaller. So now, Well,
right? Or to make it faster?
it makes it faster because, think about it, remember, reactions depend on collisions, right?
Right.
And so if you can increase the number of productive collisions, you increase the rate. Well, if you decrease that, temperature does it too. But if you decrease the activation energy, more of the collisions are going to have enough energy to get over that bump because it's a smaller bump. So that's why catalyst is effective. But the thermodynamics, the delta H part of it, is something different. Yeah. There's three things about reactions that we worry about. We worry about how fast they go, that's kinetics, which we did. The thermodynamics, which is the reaction likely to occur or is it spontaneous? That's the delta H, and entropy comes into that. We'll talk about that later. And then what does it look like when you get to the end? And that's equilibrium, which is what we start Wednesday. Yeah. Hi.
Hello, hey John.
We're shutting down.
No worries, no worries. That's good. Always double check. Make sure the lamps are out.
See, I know what I'm doing.
We always send everybody things every night for last minute.
Yeah, I know what I'm sorry.
You're good. No,
If you
you're
see
good.
me in here, you can go ahead and take off because I use this all the time.
No worries. I appreciate it. Thank you. You have a great night. You too.
Pardon? Sure.
Really? Yes, I do.
Well, density is typically.
You did?
Density is it's typically grams per milliliter, unless you're talking about a gas. And when we're talking about a gas, the volume is liters because
I didn't even get to ask
it's
my question.
yeah, because it's so low. But density is grams per mil. That's the definition of density.
Hey, Tim, I know you also have to.
Right. But then I put 1,000 mils. 1,000 mils. It was given to us in liters, and I put it over 1,000 mils. So density is a conversion. Density is a conversion factor. Density says that for example, I have 1.16 grams for every 1 mil of solution. If I have 1,000 mils of solution, how many grams is that? So this is your density. You can use that then, if you know this number, you can get that number. If you know this, you can get that number. Density is a way to get from mass to volume. Just like molar mass. Molar mass is a way, right, that if you know the molar mass, you know how many moles, you can get grams. Or if you know grams, you can get moles. And if you know grams and moles, you can get molar mass. Same here. If you know density in grams, you can get volume. If you know density in volume, you can get grams. And if you know the grams and the volume associated with those grams, you can tell me the density. So this is exactly like a molar mass calculation. It's a conversion factor. Density is a conversion between grams and mils. The units are milliliters. So you can't put liters down. I went from liters to milliliters, and then your number down here has to be in milliliters. Your number up here has to be in grams. You're welcome.
All nighters tonight.
Well, what we did, no, it's a little different because there we were just adding reactions together. The mechanisms, we're talking about the details of what's going on, exactly what's going on in each step. Hess's law is just saying that we can think of a reaction occurring in a direct step, or we can put other steps together to get to the same point. But the other steps don't have to be, and actually lots of times the other path we map out, like the enthalpy stuff that we did at the beginning of the solution chapter, where you said delta H is solution going straight, and then we break the solvent, put them together. That process, it doesn't occur. We don't take all of the solute particles and pull them apart to a gas, and all the solvent, and pull them together in a gas, and then put the two gases together. That's not how a solution is made. But conceptually, because delta H is a state function, we can create that path and add those numbers that we have together and get what the delta H would be for the real process that occurs. So I think of Hess's law as being a way to take, basically to create a fictitious pathway to get from a starting point to the ending point. You want to know what the real value is. If you can put together a bunch of artificial steps that don't actually happen, but if you can put them together and they start you and stop you at the same point, you can take all those, a cartoon, if you will, and that delta H for all of that process will equal the real one. That's completely different than kinetics, where in the mechanism, we're saying these individual steps, this is actually what happens. Yeah. The correlation is you can add reactions together in a mechanism to get the overall reaction. You can add individual reactions in this law to get an overall reaction. That's about the level that they're the same.
So one actually, that's reality.
Mechanisms is our attempt to describe reality. Hess's law is our attempt to get a real delta H, usually with things that don't actually happen, that we have delta H's.
So like, everyone thought kinetics are actually
Yes, yes, kind of. You're very welcome. Hi. Good.
I just walked in on the other one. This one, for the regular, we should say K divided by, like, K divided by K1. I remember somebody had 2 with the X right there. So whatever that exponent is, that, well, 2 times 2 is a 4. I'm sorry, I can't really show that. But you know how, like, the term of regular we got the 2 and the X up top of the exponent? Is that what we derive from there since we divided the
Yes.
K1, K2, and then?
Yes, that's exactly what.
Thank you.
Hey. No. Well, this is the way it's going to be. It's going to have a slope, and it's going to be a negative slope.
Okay, so one, first order and zero order?
Can I draw?
Yeah.
Where can I draw?
You can draw anywhere.
So if you have, and let me show you the actual graph. So if you, and this is a diagram that's in your lab manual, if you have the lab
I have the
manual.
lab manual.
So if you grab the lab manual, I'll show it to you. Here, see, here's the plot. This is in your lab manual. If you take a look at this,
Yeah.
if you plot, so if you collect data, right? So you have concentration versus time data, and so we're assuming here. So we're going to plot concentration versus time for 3 different types of reactions: a 0 order, a first, and a second. And what you get is when you plot concentration versus time, only one of them gives you a straight line. It'll be a negative slope because the integrated rate law, delta A equals negative KT plus A0. So it'll be a negative, and it's only going to be if it's 0 order data that you get the straight line. The other 2, if it's first order or second order data, if you plot this versus time, you don't get a line, you get curves.
Right. So if they give us these 2, how could, like, if they didn't give us those other 3, how could we differ?
What do you mean if they didn't give you the other 3? What if you just gave you this curve here?
Like if they just give us this red line and then they would just give us this green line, how could you differ? That you wouldn't be able to then.
Well, here's the way the problems are given. Let me show you an example. This is 2007 exam. So you're given a reaction. I showed this in class, right? So below are various plots showing relationships. So concentration versus time, it's a curve. So we know it's not 0 order. 1 over concentration versus time is a straight line with a positive slope. This tells you your data is second order. This one, if you plot natural log of A versus time, it's a curve. So only one of these 3 plots for a given set of data gives you a straight line. And it's the one that matches the order.
Okay. So then you have to memorize the inverse. Or not the inverse, but like the slopes of the other ones too. According to the concentration.
Well, the idea being is that
Is it like the whole negative K?
well, you need to know the 3 integrated rate laws,
Well, yeah.
right? And so when you memorize your integrated rate laws, right, your 0 order has a negative KT.
Right.
Your first order has a negative KT, and your second order has a positive KT. That's the
So
slope.
that's like that.
That's right. So your first order, your 0 and first order, the lines are like this, and your second order is like this because it's 1 over A.
So like this.
Yeah, so this is another example. So this one, looking at this would be a first order. This data, looking at these 3, because I plotted this concentration versus time, natural log of that concentration versus time, and 1 over that concentration versus time. And the only one that gives you a straight line is natural log of that versus time with a negative slope. The fact that natural log versus time gives you a line tells you that it's first order data. So it's a first order reaction because that's what gives you a straight line. This one is second order because it's 1 over x versus time that gives you a straight line. Yeah. I don't even get hung up on, I mean, the slope should match,
Yeah.
negative, positive, but
Just
I
the
look and say,
concept.
what did I plot? Did I plot A over time versus time, natural log versus time, or 1 over concentration versus time? And which one of those gives you a straight line tells you the order of the reaction. Yeah.
Thank you.
You're welcome. Okay? I don't have it with me here. Had someone else giving them to me so I could work them out for people.
Yeah.
Number 12? Okay, so first order reaction is the rate constant of that. And the time required of that reaction to be 75% complete. So if you look at that,
That's why I don't study well when I'm like,
we're here when we work out. We may came in later. But I think the first problem we work. So there's two ways to solve this one. The first one is, this is a first order reaction. Your total is first order, and the units tell you it's first order. So what I have is the natural log of A at time t is minus kt plus the natural log of A0, right? So if you look at this, right, I can solve this because I want to know for it to be 75% complete. So I'm going to give it a k, right? That's 3 times 10 to the minus third inverse seconds. I'm looking for a time. Now what do I plug in here and here? Well, if I start out with A0 as my